Hello everyone, my name is Brian Ip and I'm a software engineer at Square and I work on the databases team. And the title of my talk today is Operationalizing Redis at Scale at Square. So a little bit about Square. We are a mobile payments processor that builds tools and hardware for small business merchants to accept credit card payments. We build a suite of software products to help businesses grow and expand. And as I'm sure you can imagine, running these products requires us to maintain a lot of data. And we do so in a couple different ways using several different types of data stores. And as you can assume, one of those is Redis. At my team's formation, however, we were only responsible for maintaining the company's MySQL instances. Like many a startup, Square began its persistent data usage using MySQL, a battle-hardened open source piece of software that served many of our basic data storage needs. But as often happens, companies grow and their data usage patterns change. Applications may require different functionalities out of their data stores. Some high-performance apps may want to use a different data store to better serve their specific needs. Eventually, the team adopted Redis and decided to give it full parity in features to MySQL. But our path to fully operationalizing Redis required a lot of work from the team, and that is the focus of my talk today. When we made the decision to formally adopt Redis, we had a well-proven, field-tested environment to run our MySQL instances. And we were able to standardize and automate many of the processes that went into managing this environment across our many data centers. But Redis was actually in use at Square from its very early beginnings. The software was just owned by the application developers themselves. At the time, we had a monolithic design to our infrastructure, relying on a single application and a single large Redis instance. However, we evolved into using a microservices architecture and went from a single Redis instance to hundreds owned by many, many different applications. Because each Redis instance was owned by a separate team, we ended up having a plethora of different configurations. Different apps would decide to use RDB versus AOF, for example. And there were many different inconsistent memory allocations. Some applications just didn't even have a max memory set at all. And each time we needed a new Redis cluster, we would have to request and register more ports on our network. And that works well and it's fine for the first couple of apps, but as Redis grows more popular among our engineers, my team was eventually given responsibility for maintaining and owning Redis. Our goal then became to standardize the Redis environment and operationalize it so that a small team of DBAs could easily manage the hundreds of instances that we needed to run. And key to managing all these Redis clusters was automation, which we could achieve through these kinds of features. And our dream of owning Redis consisted of four basic parts. The standard setup and deployment process, a platform on which we can run Redis securely, high availability, and highly visible metrics. So the first one I will discuss is our standard setup and deployment. So at Square, we deploy all our Redis instances within LXC containers, and we limit it to a single Redis instance within each container. This allows us to have a reasonable degree of isolation from other processes or applications running on the host. Although each container still has to contend for resources from the same CPU and the same physical memory, each instance is relatively isolated from each other. But the great advantage this comes when we're writing our tooling. We can assume each Redis instance will all have the exact same environment. All Redises can listen on the same port, and it can place its socket files in the same directory. So any of our tools that run locally know automatically how to connect to Redis and find exactly where any Redis files may be located on the file system. Prior to containerization, we were running many Redis instances just on the same server, with each instance having its own directory and listening on its own ports. However, once you get past a handful of clusters, this is incredibly hard to manage. When operating a farm of hundreds of clusters, we want all our instances to be as cookie cutter-like as possible. This not only just makes automation simpler, but just possible to begin with. A disadvantage of this container model is that there's a lot of overhead to running LXC containers. Any local process that we have running on a per host basis, things like monitoring or file system management, will be duplicated across each container on the host. This can add significant overhead to running multiple containers on the same physical server, but with enough resource allocation and planning, this shouldn't be a problem. And now a short note about how we deploy Redis and all the other apps that we use. At Square, we have developed our own deployment service and open sourced it. It's called P2. P2 is a collection of tools intended to allow huge fleets of machines to participate in safe, flexible, and scalable deployment models. It was designed for Square, but is a general purpose framework that was modeled off of Kubernetes. And so that's our deployment process. Next, I would like to discuss how we handle persistence in our setup. So, long story short, we don't guarantee persistence of data. That is not to say that we don't care about the integrity of our data, but rather that given our configuration and our use case, we just don't guarantee it. First and foremost, we do not turn on RDB or AOF, and I will go into that in the next couple of slides. Additionally, we enable LRU key eviction. We have all our Redis clusters configured with a max memory setting to limit how big a Redis business can get. This is configured on a per app basis depending on the application's use cases. A side effect of LRU key eviction is that keys can get silently dropped. And we rely on this rather than, for example, erroring on max memory, because requiring a human response for each cluster is simply not scalable. However, the guidelines we set for application owners to use Redis is as an ephemeral in-memory cache. This means that caches can get cold, they can hold stale data, but the application should still be able to perform. And this makes the LRU key eviction a lot more tolerable. And if an app actually does use Redis as an ephemeral cache, then these restrictions are pretty straightforward. However, we use two popular job queue frameworks for Rails applications, Rescue and Sidekick. So Rescue and Sidekick use Redis in their implementations of job queues, and they require that persistence be turned on. However, we skirt around this requirement by enforcing that job queues be rebuildable and that jobs be idempotent. In this way, we ensure that if a job queue is lost or is in some way corrupted, we can totally rebuild it and not suffer the consequences of lost or repeated jobs. And since we do not support the Redis-provided methods of persistence, we instead implement our own form of persistence through the use of replicas and coordinated failovers. That way, in the event of a host failure, we can fail onto a healthy host. It is important to remember that since Redis uses asynchronous replication, there is still a possibility of data loss. Writes can be acknowledged by the master before being replicated by the slave, so it is important to be aware of this limitation and try to limit replication lag. So, we enforce that Redis be used as an ephemeral cache for all of our apps, even though Redis provides persistence. But we don't enable those settings, and let's first consider RDB. Redis snapshot backups in the form of RDBs is a useful way of getting a consistent view of the database at a single moment in time. RDB preserves a snapshot of the database by running bgsave, which will fork a child process which will run the backup so that the parent Redis process can continue serving clients. However, through prior experience at Square, we have found that this setting cannot always be turned on. We discovered that our servers were vulnerable to major performance hits when a bgsave was run. On databases with really large databases, forking the Redis process can often take a non-trivial amount of time to allocate the appropriate memory spaces, and this results in clients not being served. If we co-locate several large Redis instances together on the same physical server, there is a lot of pressure on the operating system to serve these requests, and downtime can be extended. Because of this problem, we turn off RDB snapshots on our active masters. We'll actually only manually trigger a BG saves when setting up a new replica, but as I'll mention later in this talk, we will reserve those to only very rare usages. We maintain replicas of all our database instances to be used in cases of failure. Since these instances need to be ready at any time, we also don't run RDB snapshots on those hosts either. We can only reliably run RDB snapshots on tertiary or lower replicas to avoid impacts to production traffic. On the hosts that can run RDB snapshots, it is important to set up some coordination so that you don't end up having several Redis instances on the same host begin a BG save at the same time. This means that Redis automated BG saves should be disabled. Instead, manual control should be used, and that can take the form of some other service. The most simple way would be to have a cron job that connects to Redis and manually run the BG save command. We have a centralized backup system that is able to coordinate with the other containers on the host on when backups should be run. In terms of persisting data, the RDB snapshot is exactly what it sounds like. It performs a snapshot. Any writes that were made since the last snapshot would be lost in the event of a server failure. So having these snapshots doesn't really serve us well in the use case of job queues because you're going to have lost jobs. However, for applications that does use Redis as a cache, these snapshots provide a quick and easy way to warm up that cache. And the second form of persistence given by Redis is the append-only log file. The AOF is a log file that saves a log of all writes on the Redis database. On startup, Redis is able to read the AOF and reconstruct its data set from replaying those writes. Compared to the RDB, the AOF is going to be a bigger file, but does offer a higher level of persistence. So AOF writes operations to the log file, but it has variables for how often an fsync will be called, which will actually flush the data to the disk and persist it. The most efficient way to run AOF is with append fsync off. And this will relinquish control of fsync to the kernel, letting it decide how often it needs to flush the disk. However, the default behavior is to run fsync every 1 second. On applications that are serving 100 QPS, that's a potential 100 writes lost in the event of a failure. On apps as low as 1 QPS, that's still a potential write lost. To call this persistent would be a little misleading, and it's dangerous for application owners to rely on this notion of durability. The append fsync always setting would guarantee us the level of persistence that we want. However, we have observed that in some of our more traffic-intensive applications, the resulting throughput is simply too low. In conclusion, we have decided that the two Redis-provided methods for persistence don't really meet up to our performance standards, so we turn them off by default on all of our active masters. So, a dangerous side effect of turning off RDB and AOF is that if a Redis instance were to, for any reason, stop and get restarted, it would come back with a completely empty data set. And as an example in this graph, I have charted the memory usage of a Redis cluster. We can see the memory usage of the master, the orange line, continually increase until it hits about 100%. At that point, some process kills it, and the memory usage drops back down to 0 when Redis restarts. And similarly, because that host was the master, all replicas slaving off of it then wipe their own data sets as well. So turning off RDB and AOF is extremely dangerous to run in production environments. But we have come up with a few controls to help prevent this kind of situation from happening. So our solution was to prevent Redis from starting automatically. And in what seems to be counter to our goal of scalable automation, we removed a lot of automation revolving around restarting a Redis instance, and instead opting for manual intervention from a DBA. When a Redis instance stops, our run it service doesn't actually run the Redis process. It runs one of our start scripts. Part of this script's biggest functionality is that it will wait for a DBA to explicitly allow Redis to start. And the DBA does that in the form of touching a special Redis start file. The start script will check for the existence of this up file before actually starting Redis. And since there are no automated processes that will create this file, it is up to the DBA to manually verify that the instance is okay to start. In this way, we avoid Redis instances unintentionally coming up with empty data sets and blowing away any of their potential downstream replicas. Additionally, when a Redis instance does come up, we do not have it configured to automatically join any clusters. It will automatically come up as a master, standalone, and has to be explicitly told to replicate off of another host. Having these two manual controls is important for us to protect the integrity of our data across a cluster. Although we do not automate these processes and instead leave it up to the DBA to perform, these steps are vital to ensuring that our data is not lost. But beyond that, we don't mind manually restarting Redis instances after failure because we don't actually care about individual nodes. We'd rather just spin up a completely new Redis instance instead of fixing a broken one. So that covers our setup and deployment, and the next part I would like to talk about is our security, namely in the form of SSL and TLS. So, unfortunately, Redis does not natively support SSL and TLS. Even though we run our Redis servers in environments that do not have access to the open internet, it is still important for us to encrypt all traffic that is going between different zones and different servers. TLS is vital to us in order to protect our security and the privacy of our data. Our solution was to use an open source software, Ghost Tunnel. Ghost Tunnel was developed at Square and is available on GitHub. Ghost Tunnel is an SSL/TLS proxy that allows us to secure services that don't natively support TLS. It offers us the ability to enforce authentication via SSL, cert, and key files. Prior to Ghost Tunnel, at Square, we used another open source tool, S-Tunnel, as our SSL proxy. But we upgraded to Ghost Tunnel because it provided us with a few benefits. And one of the coolest features to me is the ability to load new certificates without having to restart Redis or restart Ghost Tunnel. Especially because we were migrating from a non-standard environment using a variety of different certificates, we were able to hot swap in our new standard certs without interrupting traffic to Redis instances. Additionally, looking at more long-term maintenance, it makes renewing our Redis certificates incredibly easy. When certificates expire, whether on the application server side or on the database server side, we can easily reload the certificates without taking downtime. And this is exceptionally important because certificate rotation is an ongoing process that is constantly running in the background. Certs expire on a frequent basis, and we need automation for automatically reloading them with minimal human intervention and minimal downtime for the applications. So how do we deploy Ghost Tunnel on our servers? This is a diagram of our model without Ghost Tunnel. An application would normally connect to its database server through the RW service IP. That is a special IP address that we put on the server for use exclusively by the application. And the app would then be able to connect to Redis directly. But this is what the picture would look like when we add Ghost Tunnel. In our environment, Redis and Ghost Tunnel are always deployed together. With Ghost Tunnel, the application does not actually connect to Redis directly. Rather, it connects to the Ghost Tunnel server instance on the targeted host. In this example, we have the Ghost Tunnel server listening on the standard port 6379. Ghost Tunnel connects to the Redis socket. So the application would send encrypted traffic to Ghost Tunnel. Ghost Tunnel will decrypt it and send it through the socket to actually connect to Redis. The application itself can either handle TLS natively, or more often we'll see that we're running a Ghost Tunnel client instance on the application server side as well. But in our environment, we also need to encrypt our replication streams. And this, however, slightly complicates how replication is run between different Redis instances. We can no longer just simply issue a straightforward slave of command. Instead, we have a separate Ghost Tunnel client instance running on each host. Here, I have labeled it Ghost Tunnel REPL to indicate that it is used for replication. The Ghost Tunnel client is configured to point at the Ghost Tunnel app on the master instance. We have to run this Ghost Tunnel client instance on a different port, and in this example is 6380. So on the replica, to begin replication, you issue the slave of command to slave off of localhost at port 6380. Ghost Tunnel REPL will connect to the master and is able to set up the replication stream. One problem this has created for us is that it is extremely hard for the DBA to manually inspect how replication topologies are managed. On the slave, the master host and port will be listed as 127.0.0.1 and 6380. On the master, it is also impossible to tell what the slaves actually are because they'll just be listed as connecting through the Unix socket. We do have a workaround for it though. In all of our tooling, in order to build a picture of what replication topology looks like for a given cluster, we run the info command and then take the run ID. The run ID is a hash that is unique across Redis instances, and as long as the server stays up, it will be consistent between calls. Our tools then correlate this run ID with known host names so that they can build a human readable format for displaying the cluster topology. This run ID is actually what Redis Sentinel itself uses to identify Redis instances. For DBA, however, this method isn't really feasible. Instead, he would have to look at the Ghost Tunnel config files to determine what the replication chains actually are. And unfortunately, the info command does not expose the host name for the server. Otherwise, this entire process would be a lot easier. We do have an open pull request to add that in, and we are waiting on its approval. So we encrypt all traffic going between hosts, but we still have to limit user access to each Redis instance. Unfortunately, Redis does not natively support user access control, instead relying on limiting user access at a higher level, namely the application layer. On each host, we have the Redis socket available only to root, and on these machines, that access is only available to DBAs and other infrastructure engineers. Not only is access to the Redis socket controlled, but any access to it is also logged. And we have an extensive audit trail tracking any privileged commands on every host. But how does an application developer then access his or her Redis? Well, each application is granted its own set of certain key files with which it can connect to Redis. And application engineers will also have access to those certs. Since Ghost Tunnel is just an SSL proxy, accessing Redis from another host is as simple as using OpenSSL. These certs are specific to each application, so an engineer must have explicit access to that app secrets to use them. This is also how we limit applications to connecting to the correct Redis instance. Again, I would like to emphasize that the security of our data is a top concern for us. We operate Redis on servers that are not accessible from the open internet, and we enable firewalls to separate every host from each other. And it is still critical for us for all traffic going between hosts to be encrypted. So that's security, and now I'd like to talk about how we manage high availability. And we had several solutions to consider for making our Redis environment highly available, and I will go through them in this next section. So Redis Sentinel is one solution that would provide high availability for Redis. Redis Sentinel works as a distributed system to monitor the health of your Redis clusters. It provides monitoring and notifications on those metrics. And to me, what I really like is it has failure detection and can initiate automated failovers with minimal human interaction. However, the biggest drawback for our environment was that it required plain text communication between Sentinel and Redis instances. This is because each Redis instance must be able to report its own IP and port number. But because we hide all Redis communication behind Ghost Tunnel, that may not be the same IP and port number that is accessible via Ghost Tunnel. And we consider different setups that would allow us to get around this encryption requirement. For example, we considered deploying different Sentinel clusters within each security zone, and they would only monitor a subset of hosts. However, this would violate our requirement for having cross-data center monitoring and cross-data center failovers. And that would warrant a more complex solution. Another solution we considered was the Redis clustering tool, which is used to shard data across multiple Redis instances. The result is that you have a single cluster containing multiple masters and multiple replicas that each hold a subset of the total data set. But because your data is spread out across multiple hosts, single host failures have a reasonable degree of resistance against data loss. The Redis Cluster tool also provides operations for easily promoting hosts to become new masters, making required DBA intervention minimal. However, there were some drawbacks to Redis Cluster. And although consistency was prioritized in its design over availability, due to the use of asynchronous replication, strong consistency is hard to achieve unless a large performance hit is taken. And in cases of network partitioning, consistency is just not attained. And similar to Redis Sentinel, our SSL and TLS requirements simply make this option a non-starter for us. Instead, we decided to structure our own Redis topologies and write our own failover tool, which I will go into in the next few slides. But because we are still limited to asynchronous replication, we are still prone to a lack of consistency due to replication lag. However, by rolling out our own failover tool, we were able to satisfy our hard requirements for traffic encryption. So this is the standard setup of a Redis cluster for us. Our clusters consist of hosts spread out across multiple data centers with at least 2 hosts allocated per data center. There is a single master host off which all other replicas will be chained. In this drawing, I colored it red so that you can easily spot the difference. In reality, all our servers are probably going to be the same color. We also have a number of tertiary replicas, and that is to ensure that in the event of a host failure, there is a host for us to fail onto and maintain redundancy. And as I had mentioned earlier, we use an IP-based routing and failover method. We allocate an RW service IP that will be located on the master so that applications can connect to that service IP and it will automatically be routed to the correct host. We also provide read-only service IPs that will be located on the read-only replicas. And these are used if applications are able to separate out their read-only traffic from their write traffic, or if they also want to do some form of cross-data center load balancing. So as you are all aware, the industry standard term for promoting a formerly read-only replica to become the new writable master, that process is known as a failover. I, however, think that that term is scary. So at Square, we have dubbed the term a success over, and that sounds a lot nicer. So as part of the training that I give to all new engineers coming to Square, I tell them, you will often hear me and my team say, hey, we need to do a success over on your database. I tell them, you should think in your head that's a failover, but in your heart, you should feel success over. In this example, let's say that I want to do some maintenance on the current master. I have to do a success over onto one of the available replicas. It is best practice to do the create and destroy method of performing maintenance. In this case, we want to create new instances of Redis and add them to the cluster before touching the master. So the first step is to spin up these new Redis instances. And that is incredibly easy for us to do because of our P2 deployment system. We simply deploy Redis onto any of our standby containers in the appropriate security zones. And the reason why this approach, the create and destroy approach, is desirable is because it allows us to maintain full redundancy throughout the entire process, including when we take down hosts from maintenance. At Square, we treat lack of redundancy as SEVs because these are incredibly precarious and dangerous positions to be in. So when maintenance needs to be done, it is important for us to add extra redundancy before we take hosts down so that our clusters are never caught in situations where they do lack redundancy. So the next step in this process is to set up replication between our new host and the existing cluster. As I mentioned earlier in this talk, we want to avoid kicking off a BG save on our active master, so we set up replication off of one of the inactive replicas. Once the new hosts have finished syncing and have fully caught up on replication, we sever the replication chain and promote the new host to become the new master. And finally, you can take down those old hosts and recycle them and put them back into your production pool. So here's a good time to mention a minor gotcha that we ran into when trying to write this failover tool. So during the failover process, or the success over process, it is important to set your master to read only before you sever replication. That way you can ensure that replication is fully caught up and you can maintain consistency among all your hosts in the cluster. Unfortunately, Redis has no read-only setting. Our way around this is to take advantage of the min slaves to write setting. Normally, this is used to control a master accepting writes in the event of a network partition where a number of slaves may drop offline. We have hijacked this setting to use this as our read-only option. On a master, we set min slaves to write to 0 as our method of making the master writable. We then set it to some arbitrarily high number to signify that it is read-only. Since we do not reasonably expect 1,000 slaves to connect off of a single host, it is effectively read-only. On the slave, we do something similar. Although it doesn't have an effect on the slave, since we have slave read-only turned on anyways, it will prevent unwanted writes in the case that replication is unintentionally broken. Having these kinds of safety features allows us to guarantee the consistency of our data and prevent data drift between hosts. So that's what happens in the case of planned maintenance. But what happens in the case of a host failure? If, for example, your database is on fire, and not the good kind of on fire, but the bad kind, it is going to require a much faster response. The first step of any good failure response is to panic. But once you get over that, you can begin the recovery process. The first and immediate step is to perform your stoneth due diligence. That is to completely fence off your dead host. You need to make sure that that host is unreachable. Otherwise, you could be left in a position where it comes back up and begins to start serving traffic. And then we are left in a split brain scenario. Once you properly fence off your sick host from traffic, you can then promote one of the healthy hosts to become the new master, prefer, if possible, staying within the same data center and choosing the host that offers the most remaining redundancy. Here, traffic to the Redis cluster can resume, and from the application's perspective, service is restored to full functionality despite our loss in redundancy. And again, using our P2 deployment system, we can spin up new Redis instances rather painlessly. Unfortunately, we will have to take a hit by setting up new replicas off the active master. But in cases of actual server failure, this step is often necessary in order to restore redundancy. And finally, you throw away your old host, or you kick it off to some other team to investigate what happened. But what is important is that redundancy is finally restored, and at this point, you can consider yourself fully recovered from the host failure. And finally, I would wish to discuss how we monitor and provide metrics on our Redis instances. Two of my colleagues, Alex Cummins and Daniel Nee, gave a talk at Percona Live a few weeks ago about our metrics collection system. So if you want a more in-depth look as to how our infrastructure actually handles metrics, you can look up their talk on the Percona Live website. So this is a sample of a dashboard for a Redis cluster. It shows a subset of metrics that we collect. As I mentioned earlier, having these highly visible metrics is important not just for DBAs to investigate and respond to outages, but also to anticipate and prevent failures, which may be a result of software or hardware. We collect Redis-specific metrics like memory used and operations and client metrics, but we also correlate those metrics collected on the servers relating to their performance, things like general CPU and memory usage. And because we co-locate several instances together through our LXC containers, it is important for us to overlay the metrics of several co-located clusters together. That way, if there's a degradation caused by a noisy neighbor on a single host, we can easily spot the offending cluster and deal with it appropriately, rather than having to shut down a whole host of clusters that are otherwise healthy. So as an example, we had a service that was experiencing spikes in latency minutes apart at kind of irregular intervals. But because we expose these metrics and graphs to application developers, they were able to pinpoint unusually large spikes in packets being sent to and from their Redis server, even though the operations per second metric was relatively constant. They were then able to identify the errant process that was making these weird requests. This just goes to show that, as an example, even seemingly unrelated metrics can give valuable insight to the performance of the database and the application at large. And at the heart of all this is that it is important to have no dark corners within the application. Metrics must be visible throughout the application's processes, and importantly, it must be possible to correlate those metrics with those collected from the database. So that's an overview of how we use Redis at Square, and now I would like to talk for a few moments about our path forward. What else do we have to do? What else do we have to accomplish in our operationalization of Redis? So SpinCycle is my team's latest open source project. It's a tool that can be used to automate and manage our entire database infrastructure. It's still in the very early stages of development, but we look forward to releasing it and its Redis management capabilities to the rest of the community. Also, as I hope I've impressed upon you in this talk, security is a top priority for us. SSL encryption of traffic in and out of Redis is an absolute requirement. And while our usage of an SSL proxy to encrypt traffic works for us today, having native SSL support is what we believe to be the best solution. And I mentioned a few gotchas in this talk, things like the read-only setting and getting host names. At Square, we hope to have working internal patches that will allow us to enable these features for us, because ultimately, we don't want to rely on hacks to work around these issues, but have these features be natively supported. And that's it. So, does anyone have any questions? Yes.
I have a very quick question around your strategy around doing BG safe. So you mentioned earlier that it should be done on the tertiary replica. And given the asynchronous nature of Redis doing replication, how do you basically keep your snapshot data integrity with regards to the master replica or primary replica, I guess?
I'm sorry, I missed the last
one. So how do you keep the data integrity of your snapshot if you're doing it on your tertiary replica?
Oh, I see. So we do have the snapshot on a tertiary replica, which is far away from our master and often lags behind what is the current status of the database. But ultimately, we don't really provide that snapshot to application owners in that we don't want them to rely on having that snapshot as a form of backup. It's better for us to say that there just is no persistence, and in a perfect storm of events, data could be lost, which is why it's important to treat Redis as a cache and to have your job queues be completely rebuildable. So we only use the snapshot as a way of warming up the cache so that the cache could hold stale data and it could be incomplete, but it will still be there. Rather, we rely on having replicas and failing onto them in the cases of failure in order to maintain persistence.
Curious about the ghost tunnel. Thing is, if I have a Redis provision on the cloud, and if I add ghost tunnel to it, will it secure the whole thing for now? Will it do it? That's my question. I mean, I want to secure a Redis server on the cloud, and if I put in a ghost tunnel, will it do its job? I mean, is it good enough?
Oh, so this is related to our hostname issue. Yeah. So the reason why we couldn't really determine hostname is because we hide all of our instances behind ghost tunnel clients and ghost tunnel servers, so that when you connect to another Redis host through ghost tunnel, it'll appear like it's connecting to localhost or it's connecting from the Unix socket, and that obfuscates the hostname for us. If you're connecting directly to a host itself without having to go through a proxy, then you're able to just grab the hostname itself. You just know the hostname from issuing the command to connect in the first place. The real hostname issue came in when you're trying to determine replication, because when you try to connect to the master from your replica instance, you're unable to tell where that's going without having to look at your ghost tunnel configs. Yes?
Hello, I am Salvatore, Redis developers, and I would like to add a few things about the stuff you showed. One is about Sentinel. Now there is a feature when you can say Sentinel to announce a different IP and port.
Okay.
And you could use that in order to fix the problem with the SSL. But at this point you are already set up with your system, so the switch. But well, there is this feature because also a similar feature is also available for slaves in order to announce themselves to the master with a different IP port, otherwise in the info of the replication. About the RDB or AOF rewrite in master causing problems.
Yes.
When Stripe had this problem, they posted a blog post and they performed an investigation. And what I found is that for an unfortunate set of Linux kernel setups, you were using transparent huge pages. So what was happening is that instead of the 4 kilobyte pages, you used 2 megabytes pages. What this means is that after the fork, the whole process space gets duplicated after just a few requests, because with 2 megabyte pages, it's very easy just with a few random sets to duplicate the process space. And this creates the unavailability that you observed. I wonder if you are interested in testing it again with the proper setup. After this incident of Stripe, Redis was modified in order to warn the user if the transparent huge page was enabled on the kernel. Recently, JMalloc authors, the allocator, realized that this was a problem not just for Redis but for everybody else, and now there is a configure setup in the allocator so that JMalloc will not try to use transparent huge page, because yes, the page table of the process becomes smaller, but the cost is huge. And because there are a lot of users persisting on the master without problems, I'm sure that if you perform an investigation of why there is latency during the snapshotting stage, you can tune the kernel and the system in order to have no problems during assuming that this is still useful for that.
Absolutely, and it's funny that you bring that up, because last week we actually started an investigation into our usage of transparent huge pages, and we're actually discussing the benefits and which servers that we should turn it on and which servers we should turn it off. So when we do decide to disable it and try to test all of our applications on it, I'm interested to see how Redis does perform when we turn on our persistence controls. Yeah, so it's funny that you bring that up now because we actually just started investigating that too.
About the ACL, there is a proposal in Redis in order to implement ACL that I wrote some time ago, and now it's some time that I want to actually implement it, and it's quite. It's able to define different users with different privileges about the command you execute. You can also specify a key pattern to give access or not, and this is going finally to go online. About SSL, the problem is that there is a part of the user base that's extremely vocal about not adding it at any cost. Because they I understand that when this is needed, to have it externally is a big operational concern, because more moving parts, it's always a recipe for potential disasters of many kinds. However, other users using that don't need this feature in Redis, but that have SSL support elsewhere, are more skeptical. And one of the previous conferences, many people advised me not to add this because it's a source of complexity. So at some point it was believed to be something that it was possible to do at compile time. Because I believe because of Stripe intervention, at some point there was a pull request about SSL. But the pull request was like a draft, an interesting draft. However, if you are interested in performing like a review and in-house testing of this pull request, I will be very happy to work with Stripe in order to put SSL inside Redis in a so that by default it's disabled, and if it's possible to isolate the implementation in a different file, just with a few hooks in the core, we could make like a SSL target so that it's possible to switch that on and off. So maybe it's possible to do something. Well, thank you for your talk. Thanks.
Thank you. Yes. My hearing is terrible personally, so.
You talked about the failover process.
Yes.
Planned maintenance, you would stop the master taking any writes. When you do that, are you also simultaneously opening it and what's the application?
So when we turn the master off from accepting writes, we put it in a read-only mode, and then it's only the Redis cluster ends up being briefly unavailable to the application, because after we turn on read-only, we want to ensure that full consistency is met across the cluster. Because if we turn on read-only mode on the master and then promote the replica at the same time, there's a small chance for there to be some small inconsistencies. And in order to avoid that, we wait for consistency to be caught up before promoting the new host. And usually that's incredibly fast. It's almost not noticeable. Yes? Oh, okay.
You've shown that you use LXC containers for all of your Redis. I'm just wondering if you had any insight into that process of evaluating Redis on LXC, and if there's anything specific you found you had to do to make that work well.
Unfortunately, our decision to use LXC containers came before I came to the company, and I don't have that information. I'm sorry.
But there's nothing LXC specific you had to do with your tooling. It just worked with no...
More or less, it just works with our usage, yeah. Okay, I think that's it. Thanks for listening to me speak.